Yeah, the host can leave the meeting. FYI.
Yeah, okay, so we all know Akram, so you start with your talk, and then I guess if questions after the talk.
Okay, good morning everyone, thanks a lot for coming today. And today I'm going to talk about characterization and control of quantum systems using machine learning. I'll start by giving an overview of the different projects I've been working on, my PhD, very quickly, and then I'll focus on the project I've been working mostly on my stage 3. Okay, so this is a map for the different projects I've been working on, updated to the current status. So I'm going to go through each of these projects very quickly because mostly I can discuss most of these things in the last 2 assessments. The first project was efficient online quantum state estimation using matrix exponentiated gradient method. So in this project we're looking into estimating the state of a quantum system, and we want to do this estimation in the form of an online algorithm. So instead of waiting to collect all the measurements and then invert them at once to find the state of the system, what we want to do is to update our estimate after each single measurement. So what we did is we ported the matrix exponential gradient method rule from classical machine learning into the quantum domain, and then we proved statements about the convergence of the estimate, and we did numerical analysis, and we showed like that using this method is as accurate as using the standard techniques such as maximum likelihood and least squares. And in terms of efficiency, we showed that this rule actually is more efficient than the other techniques because it scales as d power 3 instead of d power 4, and the results were published in New Journal of Physics last year. This was in my first year. The second year, I started working on multiple projects. The first one was in collaboration with the Quantum Photonics Lab at RMIT University in Melbourne. And in this project, we were looking into the problem of characterizing an integrated photonic circuit where we have an array of waveguides, and if we have the light going to the input, it propagates till the output, it gets coupled the neighboring waveguides, and by applying voltages on the electrodes across the waveguides, we can change the behavior of the propagation. And because of the electrical properties of the chip, there are distortions that are introduced when you apply the control pulses, and these distortions are very difficult to characterize because physically you cannot measure arbitrary voltages in this chip. We can only measure optical power. So we developed a machine learning based algorithm which is formed of a gray box, and I'm going to discuss more later about gray boxes. So the idea is we split the model into parts that are just standard layers like neural networks, and other parts which are custom layers that implement particular formulas. In this case, these are the laws of quantum mechanics that we are sure of. And we were also able to control. So in the problem of control is finding the set of control voltages such that we can implement particular quantum gates. So this was, the results were very exciting because first of all, here what we have is a sequence of quantum gates. So we can find the control voltages to implement this sequence. And this is good because if we have like non-Markovian effects, for example, if some gates, like if some gates will depend on what the status of the chip was before I'm implementing this gate. So the control algorithm can actually find the optimal set of control voltages. The other thing is if you see here in the figure of the control voltages, we can see that these non-idealities are there in the pulses, so that they have a counter effect on the distortions that are already introduced by the chip. The results were published in Quantum Science and Technology 2 months ago. The next project is about spectator architectures for spin qubits. This is an Uzumuri project in collaboration with UNSW and Griffith University. and we have also partners in the United States, but I'm mostly working with people from Australia here. And in this project, we are looking into the spectator architecture of a qubit. So in this case, we have our qubit, our data qubit. This is the qubit where we perform all the operations. And we have another quantum system, which can be qubit or qudit or any other system that's located physically near the data qubit. And what we want to do is, by measuring the spectator qubit, we can infer some information about the noise that's underlying both of them. And if we know some information about the noise, we can then implement some optimal control algorithm to control our data qubit. And in this project, I've been working in two parts. The first part is just implementing standard techniques, helping experimentalists in the lab, and the other part is a research part, and this is still ongoing, and probably the results of these things will not be included in my thesis, but I'm willing to work on until I finish my PhD. The next project is about characterizing orbital angular momentum photonic systems. This is done with collaboration with experimental group at University of Queensland, and this is mainly an experimental realization of this algorithm. So we didn't do much in this project. It's mainly the experimentalists are trying our algorithm. We helped a little bit in the theory to match the algorithm with their experiment, but mainly this will be mostly on the experimental side. The final projects, which I'm going to talk in detail about, is about going beyond quantum noise spectroscopy, and this is done in collaboration with Griffith University. It started as a part of this project, but then it's completely finished now and it's on the archive, and I'm going to talk now in detail about this project. Okay, so this is our project. It's about modeling open quantum systems, and this is done with Gerardo and Chris. And I'm going to start with a theoretical model about what's an open quantum system. So let's start with a qubit, and this is just a free evolution. So if we start with Hamiltonian like this, and we are fixing the evolution to be from 0 to t capital, then the effect of this Hamiltonian is just a rotation around the z-axis. Okay? So if we start in a state like this state, which is the eigen state of the x operator, so it's along this direction, then the evolution is simply that the qubit just rotates around the z-axis, and the speed of rotation is related to the angular frequency, which is omega. Now, if we have noise in the system, the noise comes from the system interacting with the environment. So we usually have a Hamiltonian for the environment and another Hamiltonian for the system-environment interaction. But then we can reduce, in many cases, we can reduce this to a classical stochastic process. So beta of t is a stochastic process that represents noise. And so the Hamiltonian becomes also stochastic. This means that if I do the experiment, I observe the evolution during this time interval, we'll get some Hamiltonian. If I repeat the experiment, I will have a different realization, and so I'll get a different Hamiltonian. And these realizations will follow some statistics, and there are lots of statistics we can study. One of them is the autocorrelation. So the autocorrelation is defined as this quantity is the expectation of the noise at tau 1 and tau 2. So it's like a measure of how the samples are correlated in time. And this is the definition. If the noise is stationary means that the statistics do not depend on time, the distribution is constant in time, then we can actually reduce the definition of the autocorrelation function to this definition. So now it depends only on the shift between the two time instants and not particularly what these time instants are. And if we Fourier transform the autocorrelation function, what we get is the power spectral density, and this quantity measures how much power of the noise is located in a particular frequency range. In other words, if I integrate this quantity over some frequency interval in the frequency domain, I get the power of the noise in this interval. Now, what does this? What's the effect of the noise on my qubit? Well, it causes decoherence. So what happens is that we lose the off-diagonal elements of the density matrix of the qubit. And so eventually, after some time, we'll converge to the completely mixed state, which is at the center of the Bloch sphere. This means that our qubit is no longer a qubit. It becomes a classical bit. And to characterize this decoherence, we define this quantity, and this is simply the ratio between the off-diagonal element at time t divided by the off-diagonal element at time z. And notice here that we are taking the expectation over beta because, as I mentioned, this is a realization, a particular realization of the noise process. So every time I repeat the experiment, I have a different realization. So to characterize this thing, I need to average over all possible realizations. And this quantity is very important because this characterizes the lifetime of the qubit, which is called the T2 time. The T2 time is just the log of this quantity. And it's important when we are designing quantum computers because this tells us information about the maximum circuit depth I can have. Because if I want to implement some quantum gates, I have to make sure that I execute all these gates before my qubit dies. So it's very important to calculate this quantity. And theoretically, it's hard to calculate it unless we do some assumptions. So for example, if the noise is Gaussian, zero mean and stationary, then we can show analytically that the coherence is equal to this quantity. Now the problem is, if you look here, we are integrating here over the power spectral density of the noise. If we have noise such as 1 over f noise, and this is very common in lots of systems, like in electronics. This is a problem because if you see this integration, if you have 1 over f, the value of this integral will be very high, and so the coherence will be very small. So we quickly lose the qubit. So this is like a major problem. However, there is a solution. The solution is we do control. So what we do is we apply pulses on an orthogonal direction. So this is pulses along x, and they take this form. So they are instantaneous pulses. These are Dirac deltas, and they are placed at t1, t2, and so on. These points are points inside the interval from 0 to t, and all of these pulses have power equal to pi. So these are pi pulses. And we'll see the effect of these pulses now, but first we need to define the switching function. The switching function is simply, it starts with the +1, and whenever I apply a pulse, it changes the sign, -1 + 1, -1 + 1, and so on. So it just depends on this time instance. And we can show analytically that the coherence in this case becomes this expression. So it's e power -12 the integration of the power spectral density multiplied by y capital of omega. This is just the Fourier transform of this switching function. And we call this quantity the filter function. So if I know my pulses and where I place these pulses, then I can calculate the switching function, do a Fourier transform, calculate this. Now this is very nice because I can now design a pulse sequence. So if I choose my pulses such that the overlap between the power spectrum of the noise and the filter function, if this overlap is very small, then the integral will be very small, and thus will have a high coherence. So it's like I increased the lifetime of my qubit. And this is the base of designing lots of these sequences. This is like a whole field in quantum control, which is finding these sequences like CPMG, UTT. All of these sequences differ from one another where I place the pulses. And the reason behind this is there is no single pulse sequence that will increase the lifetime of the qubit for any noise, because you can see here it depends on the noise. So every type of noise will have a different spectrum, so I need a different sequence to mitigate its effects. So, and you can see here from this animation is that the qubit keeps changing because I'm applying these pulses, but overall it's not decohering anymore towards the center of the block sphere. So in a sense we increase the lifetime, and this is what we call also dynamical decoupling. So yeah, this is good. The same idea actually can be used in a different way. We can do noise spectroscopy. Noise spectroscopy means that I want to estimate the power spectrum of the noise. So sometimes in the experiment, I don't know actually what this power spectrum looks like. So we can use the same idea, because again, look at this equation. The coherence can be measured in the lab. Like this is something an experimentalist can do. It's just the expectation of the X operator with the initial state is the eigenstate of the X operator. So this is something that could be measured, and so this number is known, and the filter function is also known because I'm the one who is applying the pulses, so I know where they are located, so I can calculate this. And therefore, we can do an algorithm which was first proposed by Alvarez and Suter in 2011, where we form like a system of equations. We apply different pulses, measure different coherences, and from this system of equation I can solve it and find the unknown, which is the power spectrum. So it's like I'm going to get samples from the power spectrum of the noise at different frequencies. So this looks nice because we can characterize the noise in the system, and if I characterize the noise in the system, I can then design optimal pulse sequence to mitigate its effects. The problem, however, is, remember, the way we derive this equation is three assumptions. We have to assume that the noise is Gaussian, zero mean, stationary. So this is for the noise. And for the control, the pulses have to be instantaneous. If these assumptions do not hold, then this formula does not hold. Okay? So we thought, okay, let's try to generalize these things and use machine learning. So in order to use machine learning, we have two methods. The first method is to use a white box, which is exactly what I just described, just different language. So what we have is like a model with some unknown parameters. The unknown parameters is the samples of the power spectrum of the noise, and we have a training set consisting of a sequence, like a set of sequences of like CPMG or any dynamical decoupling sequence, and the target is the coherences that I measure in the lab. And by doing the training of this model, I want to minimize the error between the prediction of this model and the actual coherence that I measure in the lab. And so when I do the training, if I look into these numbers inside the model, this is just the samples of the power spectrum. On the other hand, we can go like in other direction, which is use a black box. So here I mean just put a huge neural network, and we'll do exactly the same. So we'll have a set of sequences in the input, the measured coherences at the output, and we do the training. However, in this case, there is no physics. Like the model doesn't even have to know that this came from a qubit. It's just trying to fit some numbers from the data set. So we have two extremes. The first extreme here is this gives some physical insight because the power spectrum is an important physical quantity. If I know the power spectrum, I know lots of things about the noise. But the formula itself depends on the assumptions. If the assumptions are not valid in the experiment, then it's not correct. On the other hand, this has no assumptions at all, but then there is no physics. I cannot know anything about what's happening inside the model. So we want something in between. So what we want to do is to design a general framework. This framework should be free of any assumptions on the noise and control. I don't want to assume that the noise is stationary, Gaussian, and so on. And also the pulses, because like instantaneous pulses don't exist. In the lab, I can only generate pulses of finite width, like Gaussian pulses that have finite width. I cannot just put a Dirac delta. This does not exist in an experiment. So I want something a general framework that's free on any assumptions. At the same time, I should be able to estimate physical quantities, so I cannot use just a black box. We want it to be easy to be implemented experimentally. And also, this framework has to fit within the literature of quantum control. Like, we can use it to do dynamical decoupling or quantum control, whatever. And so the way we go is to use a gray box approach. So, to do a gray box approach, which is a mix between a white box and a black box, we have to start with the theory. So, I'm going to go quickly through the derivation of the main formula that we are going to build our gray box upon, because I think it's important to mention. So this is like a generalized Hamiltonian. It's the same Hamiltonian we saw before, just we have here pulses in x and y and noise along all directions. And just, this is a revision in quantum mechanics, so the evolution is the time-ordered exponential of this Hamiltonian. And if we want to calculate the expectation of any observable O, like Pauli's, for example, x, y, and z, then it's just trace u, rho, u dagger, O. And here we are taking classical expectation. So this expectation is over the noise, because remember, these are realizations of noise, so my Hamiltonian is stochastic. So if I want to calculate the expectation, we should also take an expectation over the noise. Now the problem is, if I don't know the noise, I cannot do this calculation, right? Because I don't know what is beta in the experiment. So this will be difficult. So ideally we want to split the effect of the noise and the control. And the way we do it is to move to the interaction picture. A very quick reminder, we have three pictures to study the dynamics of a quantum system. We have the Schrödinger picture, in which the state depends on the time and the operators do not depend on time. This is like the usual picture we work with. We have the Heisenberg picture, which is the opposite. The state is constant, but the operators are time dependent. And then we have the interaction picture, which is both of them depend on time. And they are all equivalent. They are all equivalent. Why? Because if we calculate the expectation of an observable, it will be the same in the three pictures. It's like the exponential factors cancel out and we get the same result for the three. And the expectation of the observable is the thing that we could actually measure in an experiment. So we're going to move to the interaction picture, and there is a standard recipe that we can follow. The first step is to split the Hamiltonian into two parts, H0 and H1. So why did we split it like this? Because these terms are the terms that we know. These are the pulses that we are applying with the qubit, so we know what are these pulses. And H1, these are the things that are unknown. Okay. So the recipe says, if we want to do interaction picture, we start by defining u0 of t, which is the time-ordered evolution of h0. It's like I'm solving Schrödinger equation under h0 Hamiltonian. So this is the first step. The second step is to define h interaction, and this is just the conjugation of h1 with u0 dagger. And if I define h interaction, then I can define u interaction, which is the time-ordered exponential of h interaction. And if we do this, we can actually show that the evolution can be written as the product of u0 and ui. Okay? So it's like we split now the effects, like this one depends only on the control, this one is the unknown thing. And so when we calculate the observable, it's just the same equation, just expanding u in this form. Now, this is not very suitable, because if you look here, we still need to calculate the expectation. So if we take the expectation inside, the expectation is with respect to the noise, so O and U naught are constants. So if we take the expectation, we'll find that it will depend on rho 0. Because like when we do the sandwich, it will be inside here. So if I want to calculate the expectation, it will depend on the initial state of my qubit, which is something that I don't want to do. So we're going to do a trick. We're going, instead of using the interaction picture, we use a modified interaction picture. And this is like a very neat trick. What we do is, we go back to this result, and what we do is multiply by u dagger u, u0 dagger u0. So this is just identity, because u is unitary. Okay? So I didn't do anything, I just multiplied by the identity. However, if we look now at this part here, we have UI conjugated by U0, and it turns out if we do the math, that if we define UI tilde to be this time ordered, but this is like a reverse time ordered. So when we expand, remember when we expand the time ordered, we expand in an infinite series, and then we have to make sure that we are taking, like we are having the time order increasing. This is the time order is the opposite, decreasing. And what we get is exactly what we wanted to have, is that row 0, because now if you look, this is UI tilde, this is U0. Now we get row 0 is conjugated by U0. This is what exactly we wanted to do. The final trick is, very quickly, we apply the cyclic property of the trace. So you move O and then we move UI tilde, and what we get is this form. So we take the expectation, these terms do not depend on the noise. This term depends on the noise. I will call this term VO. Now this is very, very nice formula, because if you look here, this is exactly what we know in a closed quantum system. Remember, if we have a closed quantum system undergoing an evolution, then the observable is just U0 rho, U0 dagger times the observable. So it's like what we have extra here is this operator VO. So it's like we reduced all the effects of the noise, the dynamics of how the noise interacts with the system, into just one operator VO. And this VO, like remember, O is just an observable, like Paolo or whatever. So it depends on the observable, it depends on the noise, and on the control, because in the definition of UI tilde we have conjugation by U0. And this is like a very suitable formulation that we can use for as a base for a framework, because many problems can be expressed using this formulation. For example, if I want to do dynamical decoupling, the problem becomes as follows. Find the optimal set of controls such that VO is equal to the identity operator, and this evolution is just the identity evolution. So now I can formulate the problem of designing pulse sequence as this optimization problem. If you want to do a quantum control, which means I want to implement a quantum gate, it's similar. I want V0 to be an identity, and I want the evolution to be the evolution defined by G, where G is some desired quantum gate. And if I want to do noise spectroscopy, if I just want to find the power spectrum, then what I want to do is to find the power spectrum given VO. And there exist in the literature protocols that implements this exactly. If I know VO operator, I can calculate the power spectrum. So this seems like a nice framework that we can use. And the problem is calculating VO. So VO is like the most central operator here, but it's actually very hard to calculate. This quantity here is very hard. And again, we have the same problem. If I want to calculate it analytically, then I have to have assumptions on the noise. Otherwise, it's too hard to calculate. So this is where the point where I can start using machine learning. So the idea is, I'm going to skip this. We are going to use a black box to estimate this VO operator only. And we're going to use white boxes for the other terms, and so the overall structure will be a gray box. So when we use this construction, then I will be able to estimate VO, which is the important physical quantity, and at the same time, I have like the other parts of the quantum mechanics that are just implemented. I don't have to learn them from the data. And so we developed the following structure. It looks complicated, but it's fairly easy. Just the implementation of the equation I just mentioned. So we have here two paths. The first path is a set of black boxes, some neural networks and GRUs and so on, that generate some parameters. And these parameters are essential for constructing the VO. It's like for a qubit, VO is just a 2x2 matrix, so I can actually completely define them by 4 numbers. And so I learned these 4 numbers. This is the black box. And then I have the other direction, which is the white box direction, this is where I construct the control Hamiltonian and the control evolution. And then these layers calculate the trace. Trace VO, U rho, U dagger, O. So these are just the measurement layers. And here we have 18 of them. Why do we have 18? Because to completely characterize the dynamics of a qubit, we need to measure all the Paulis for all possible eigenstates of Paulis. So we have 6 eigenstates. Each eigenstate, we can measure 3 Pauli operators, so the total is 18. So I have 18 of these layers. The input to this model is just the parameters of the pulse sequence. And with this construction, the output will be the expectation of the observables. And so when I do the training, the parameters of these black boxes will be enforced to generate some numbers here that makes everything correct, like to minimize the error. And then, because I'm writing the software, then simply I can look at the output of these layers. And the output of these layers will be the estimation of my VO operator. So here, this is Vx, Vy, and Vz. And as I mentioned, if we know these operators, we can know a lot about the dynamics of the system. And so we did the numerical simulations for this. We generated a set of, we generated 6 data sets. So they are just different cases, like the noise in Z, the noise in X and Z, the control, and so on. So different cases. And the source code is available, open source here. And this is the result for the MSE, so mean square error for the coherence, for the expectation of the observable, for the different data sets. And as you can see, this is for training. Okay, so the model shows like very good performance. It was able to predict the observables for pulses that were not in the training set. And you can see the MSE is very small. So this plot is like the distribution of the MSE. So this is maximum, minimum, and average. And this is like the distribution. And there was very nice observation is that for the last 2 data sets, they are closed systems. So in these last 2 data sets, there is no noise, there is no beta at all. And when I was checking the output of the layers, the VO layers were actually, the 3 of them were producing identity, almost identity. So it's like we have an artificial physicist. So the computer was able to discover that, oh, this data comes from a closed system. So it's very nice. It seems this is a very good approach. The second results we have is how to use the trained model. So we trained the model with the observables, and now we use it to do standard tasks in quantum control. The first one is doing noise spectroscopy. Remember, the way we do noise spectroscopy is we need to estimate the coherences and then invert the equations. So the coherence again is just applying, it's just measuring the x plus eigenstate with the x operator. So we can use the model to predict the coherences, and then we can reconstruct the spectrum. And you can see the estimation is nice till some point. This has nothing to do with the training of the model. This is something related to the estimation of the power spectrum. This is a standard problem. If I want to probe the spectrum of the noise to a higher frequency, I have to apply more pulses. But because I'm limiting the time interval, so I have, like, I'm fixing T capital, so there's a limit on the number of pulses I can apply per interval, and so I can only estimate up to a certain point. So this is something related to the estimation of the noise spectrum, and it's not related to our algorithm. But still, we can see that during the points, like for lower frequencies, we can see that the estimate is almost good. The second thing is doing quantum control, which is very exciting. So because we have a trained model and I can estimate each of the observables, then I can do quantum control. I can just write a numerical optimizer that finds the set of pulses such that the fidelity between Vx and identity is as high as possible. Like, ideally we want this to be 1. The fidelity between Vy and I, also we need this to be 1, and the same for Vz. While for the control, I want the control unitary to be as close as possible to the gate that I want to implement. And so we tried with a universal set of quantum gates like identity X, Y, Z, H, and rotation about X. And as you can see here from this table that all the fidelities are above 99%. So this is like very promising that we can do quantum control and using the trained one. And this is an example of the pulse sequence that we explained. So this is for dynamical decoupling. Dynamical decoupling is equivalent to the identity gate. So I don't want to do anything, I just want to cancel the noise. So you can see here that we can find some pulse sequence that have, so this is like not standard, like the CPMG or whatever, but it's interesting to see.
So what does H show? What are the amplitudes?
Yeah, so this is, in this case, we have noise along, this was using the model trained over the data set of noise along Z and pulses along X only. So we have only pulses along X.
So that's the magnitude of the rotation that you apply. Okay, so it's no longer just flipping between plus and minus pi anymore.
Yeah.
Now it can be arbitrary values.
Yes.
I see. Right.
And this is for the Hadamard gate. So it's nice because now we are solving like like for this example, we are doing two things actually. We are mitigating the effect of noise, we are cancelling the effects of the noise, and at the same time we are implementing a quantum gate. And we can find like one pulse sequence to do the two things at the same time. So this is very interesting. Okay, so to sum up, we have three approaches we want to apply generally machine learning in physics application. The first is the white box, which is like curve fitting. I have a model, I have some data, and I want to fit this data to the model. And this works if I'm sure that the assumptions in the model are consistent with the experiment. The other extreme direction is a black box. So just put a huge neural network, and then we cannot know any physical insights about what's happening. And the model doesn't even know that this came from a physics experiment. And we have the gray box approach, which is in between, where we can mix the use of black boxes and white boxes. And this is like a good thing because we can still calculate some important physical quantities. We showed some promising results. So in general, what I focused today is on using the gray box to study the dynamics of an open quantum system. And what we had in the previous project, the photonic circuit, this was a closed system. So the approach, this gray box approach, can be used for like open and closed quantum systems. So it has wide applicability. Particularly for today's project, this is very can be a start for lots of interesting directions. So our focus during this project was to prove the concept that we can do this, but there are still lots of things we can do, like optimizing the black boxes. I didn't look into, like the numerical results can be enhanced more. We can use the same framework to study dynamics of higher dimensional systems like qubits or multi-qubits. We can use, there are lots of techniques in machine learning that we can try, like if we have missing data which corresponds to the case where we cannot do all the measurements. There are techniques in machine learning that we can use to still be able to learn the model, given that there's some missing numbers in the data set. So there are lots of extensions that we can do. In terms of theory versus experiment, it's very important to do theory. We wouldn't be able to reach, like to implement this framework without doing the quantum calculations and the small mathematical tricks. So it's very important to do theory and know what's exactly the assumptions, what's valid, what's not valid, and so on. We need experimentalists to help us. Like one of the major difficult parts in this project was generating the data sets. It took a very long time. It was hard to, like there were bugs in the code, and it was like a major part. And this is not the usual thing in machine learning. In machine learning, we start with a data set and we start designing our algorithm based on it. In our case, we don't have data sets in the quantum community, so it's important that, like if I have a data set from an experiment, then I can focus on optimizing my algorithm on this data set, rather than focusing on how to generate the data set efficiently, okay? Yeah. So what I'm going to do next, the paper is available on archive, so probably you need to submit it to some journal. The ongoing projects, I'll still be working on these projects. Mostly they will not be included in my thesis. So my thesis will be the three main projects: the MEC algorithm, the photonic circuit project, and this project. And so the rest of the things will probably be just papers. Then I'm going to start writing the thesis. I think it's time. And yeah, because I'm finishing this year, so I'm starting to look for a postdoc position. Please send me if you find any position. And the last thing, because this is my final CA, so I want to do some acknowledgements. So first, I want to thank Dr. Marco Tumamico. That I'm very grateful to him, and like I'm very happy that he believed in me and trusted me to be a student. I'm very happy, and I'm also happy that he gave me freedom to choose my research projects. So thank you very much. Next, I want to thank Dr. Christopher Ferry. Thanks very much for your help, and you opened me lots of opportunities to collaborate with lots of groups in Australia. So thank you very much. I'm really grateful to you, and I'm grateful for all the support for traveling and visiting universities. Next, I want to thank our collaborators from different groups in Australia. And then I want to thank my family. I want to thank especially my mom for supporting me all the way and being patient while I'm away during the time that she needed me. And I want to thank my dad also for supporting me, and especially for finishing the paperwork in Egypt that we didn't manage to finish before traveling. And finally, I want to thank my friends that I'm very happy that I got to know, and I hope we keep in touch after I finish. And with the acknowledgements done, yeah, I think it's the end, and yeah, thanks, and if you have any questions.
Well done.